Hi, and welcome to our first learning video for OLI Mod 12. We are starting with our regression analysis in this module, which is attempting to describe or come up with an equation for the relationship between our two variables that our correlation analysis revealed existed. If, of course, your search for a relationship using a scatter plot and a linear correlation coefficient told you there was no relationship between those variables, then you would not move on to regression to try and describe that relationship because it doesn't exist. But let's talk about when a relationship does exist. What is going to be the line that fits that data better? How will we describe that? So that's the first thing that we're looking at here. We've got 5 ordered pairs and then 2 lines through those same 5 ordered pairs. This does match the graphic that is in OLI in this section. Our goal with coming up with this equation and why we do this analysis to begin with is to make predictions of one variable using the other. So for instance, we might wonder, what is our best prediction of y when x is 17? So let's take a look at how answering that question goes along with these 2 graphics that are here. So an x value of 17 would perhaps be about there. Just from a visual standpoint, using this line to make the prediction means that we would look up to the ordered pair on the line where x is 17, and we would get the y coordinate corresponding to that. So from the line, it looks like maybe this estimate is somewhere around 9, but my lines are all crookedy, so that certainly is not exact in any way. If we want an exact value, we would use the equation for that line, and in place of x, we would put the number that we have, 17. 0.3 times 17 plus 4.36 gives us an answer of 9.46. So the y coordinate at this point, 9.46, has created an error because we have an actual piece of data right up here where the x coordinate is 17 and the y coordinate is 14. So this distance right here is our error. And we're concerned with vertical distances between our points and the line because changing that vertical distance or moving along the vertical axis is where we find the values of our response variable. And that's what we're concerned with, is predicting those values of the response variable. So this distance, the distance between the actual data value and the predicted value on the line, is our error. And in this case, we would need to correct that error by adding 4.54 to our prediction. 9.46, our predicted value, plus 4.54 gives us the actual variable value of 14 for when x is 17. Let's take a look at the other line. So again, making a prediction over here, we would go through the same process. So 17 is about there. We look up on the line for the corresponding ordered pair, and then we look across to find our predicted value. And this time it looks like maybe that's around 11. To get the exact value, we put 17 into our equation for the line in place of x, and this time it comes out 11.42. But again, we've made an error. Here is that same point, 17, 14. This distance is our error. So the way we correct our prediction down here on the line is by adding 2.58. Our predicted value of 11.42 plus 2.58 is how we get the actual response variable value of 14 when the explanatory variable is 17. So all of the errors for points above the line are all going to be positive. All of the errors for points below the line are going to be negative, because to correct this incorrect prediction, we would have to subtract something. We would have to move back down. Okay, so each of these errors can also be called a residual. So errors and residuals are the same thing. What we're trying to do is minimize these errors. So in deciding between which of these two lines is best, what we're trying to do is figure out which of these lines produces the more minimal amount of error. But to get a total sum of these errors, we can't just add them all together, because those that are positive will offset those that are negative. We're going to handle this obstacle in exactly the same way we handled it when we were summing up deviations to get the standard deviation. We squared each of these values. That's what we're going to do here, is square each of these errors or residuals. We're doing it for the same reason we did back in standard deviation, to put a little bit of emphasis on those points that are far away. Any very large residual or error like this one will carry a little more weight when it gets squared than a smaller error will, like this one. I've brought up the bottom picture here so we could take a look at how these squared errors are represented. So in our picture here, the residual or the error was this vertical distance. To square that value, well, it can be represented by the area of this square. One side times the other gives us the area of this rectangle, and it gives us the squared area. It gives us the squared error or the squared residual for this point. So the line that fits our data best, which is called the regression line, is the line that has the smallest possible sum of squared errors or residuals. So the one of these lines that fits the data better would be the line that has the smaller sum of squared residuals, the smaller sum of areas of those boxes. I actually think it's still a little bit difficult to tell, even from that visual representation of the squared areas, which line fits better. But we're going to move on to take a look at the one line that fits best, and neither one of these is it.